So, uh, hello everyone. This is Sakib Mahmood Khan. I am the Assistant Director for the Center for Connected Multimodal Mobility. And today I'm pleased to introduce our distinguished speaker, Dr. Mashrur Ronnie Chowdhury. So before reading his bio, I am just giving some guideline for this webinar that we will have a follow-up question and answer session. So if you have any question, please feel free to type it in the chat at any time. And our moderator, Charlotte, she will read it in the question section, or you can raise your hand and ask the questions directly to Dr. Ronnie Chowdhury. So Dr. Mashrur Ronnie Chowdhury is Eugene Douglas Mays Professor of Transportation at the Glenn Department of Civil Engineering at Clemson University. He is also a professor in the Department of Automotive Engineering and Division of Computer Science at the School of Computing. Dr. Chowdhury is a founding director of the USDOT Center for Connected Multimodal Mobility. He is the co-director of Complex Systems Analytics and Visualization Institute, CSAVI. His research focuses on transportation cyber physical systems security, navigation of connected and automated vehicles through in-vehicle sensors, and external connectivity with digital infrastructure, heterogeneous wireless communications, distributed machine learning on the edges, cloud edge computing collaboration in the CPS, and safety risk analysis for autonomous vehicle operation in a mixed traffic system. Dr. Chowdhury has published over 100 peer-reviewed journal papers, 85 peer-reviewed conference proceeding papers, 4 textbooks, 9 book chapters, and 7 research articles in widely circulated professional magazines. He has developed multiple software for connected and automated vehicles like AutoNavi, CVDev, CVGuard, PMS Gen, and POSH. His leadership in smart city research and development is evident by his close industry and public agency collaborations. He is an alumnus of the National Academy of Engineering Frontiers of Engineering program. He is a member, he is a member of the Transportation Research Board Committee on Intelligent Transportation Systems. He is also a fellow of ASC and a senior member of IEEE. At this time, I would like to turn it over to Dr. Ronnie Chowdhury. So, Dr. Ronnie Chowdhury, we are very excited and we are ready for your talk.
Thank you, Dr. Sakib Khan. Thank you very much. So today my talk will be on safety advancement through connected and automated vehicles. So we'll discuss the projects that we are doing and the future direction and the issues that are associated with safety of connected and automated vehicles. So first, just on the definition point, what is a connected and automated vehicle? So we have connectivity in the autonomous vehicle. So we can have just a sensor-based autonomous vehicle, and so it doesn't have any external connectivity. It has connectivity within the vehicle, but no external connectivity. And then we can have just a vehicle which is not autonomous, but it's connected. So it's connected around it. So it has a 360-degree connectivity around the vehicle. So it is broadcasting information around the vehicle. That's connected vehicle. And we can achieve it through different communication technologies. So, but when we combine the sensor-based autonomous vehicle and a connected vehicle together to make it a connected and automated vehicle, then it becomes a data-driven and information-aware connected and automated vehicle. And that's what we see as a future, an autonomous vehicle that is connected. So we can improve the functions of an autonomous vehicle by having it connected with the external world. And also it improves safety and security of the connected and autonomous vehicles as well. And it reduces cost. So we may not have to rely on sensors that much. So there also there might be some redundancy with connectivity. So we can reduce the workload on the sensor. So it would be a lower cost option. So that is our future, connected and autonomous vehicles. And that's where we are going with our safety propositions in this area. So what are the safety, why we need connected autonomous vehicles to improve our safety? So 94% of the serious crashes are due to human error. So when we have an autonomous vehicle, we are taking away the human decision making or human error from the vehicle. So that might reduce a significant number of these crashes, the serious crashes. And also another point, the CAV technology could save Americans 76 billion in crash-related costs per year. So it improves safety. So as we are taking out the human error, and also it will help us to reduce costs in terms of the crashes occurring every day on our highways. So the CAV safety applications, I like to start with this slide because that's what we did whenever we are going for any connected autonomous vehicle application. So this is a great resource. This is a guidance from US DOT, the ARC IT. So it is available. It's a free access to the website. It is maintained by US DOT, and it is sponsored by US DOT, and it is maintained by my former employer, Iteris. So, and you can see that, so first, when you go to the website, look at the service packages. So when you click onto the service packages, those are actually the applications. So you can look at what are the applications related to connected and autonomous vehicles. So you can look at that. So, and then, and you can then navigate the site to find applications related to connected and automated vehicle safety. So the next. So this is what we will find in terms of applications. So there are two application categories that where you'll find a lot of safety applications. One is a vehicle safety application. So you will see what are the applications. These are just some general highlights of the application. For example, situational awareness. The autonomous vehicle knows what is around it. Automated vehicle stop sign or connected vehicle stop sign gap assist. So at an unsignalized intersection, you can run this application to improve intersection safety. And on the left of this slide, you'll see that what words were more prevalent in this application. For example, warnings, cooperation between vehicles, cruise control, information dissemination. So these are the words that were most seen in these applications. So if you're starting with the safety of connected autonomous vehicles, this is a great place to start. Look at the applications, and also it will give you the requirements that are associated with each of these applications. So whenever I start with any connected and automated vehicle application deployment, I first look at the website. I look at the what is there in ARC IT. So that is my base point or base information, and then I go forward from it. And you can find really good safety information. So, and now there's another category of applications where you'll find a lot of safety information, how connected and automated vehicle can improve safety. So here's some of the major applications: emergency call tracking and dispatch, for example, emergency response, vehicle emergency response, disaster travel information. So all are related to public safety. So you can also look at the public safety applications. And on the left, you'll see what are the major words that are prevalent in these applications. And as I mentioned in the earlier slide, and you can also look at the requirements. So in order to deploy this one application, for example, stolen vehicle recovery, what are the requirements? So that could be a starting point. Either you're doing research or thinking about deploying. So you could start with the requirements. And it has also information about whether any standards exist for this application and where the standards apply. So this will be a very good resource for anyone in research or application. So now also tool that is available, actually two tools. You can use this ArcIT side. There are two software tools. One is called RADIT, the Regional Architecture Development for Intelligent Transportation, RAD-IT. So you can use it to develop regional ITS plan. So this software is a very convenient to develop a regional ITS plan, and where you have safety projects embedded in the regional architecture. But one, if you're developing any connected and autonomous vehicle project, so I would say that the SETIT is very convenient. We use SETIT all the time to develop project architecture. So you can use SETIT. It's a systems engineering tool for ITS. It integrates drawing and database tools with ArcIT. And so it is a very convenient tool to develop project architecture. So you want to develop a pilot, you want to develop a test bed. So this is a very convenient tool. So when we developed our test bed in Clemson, the 3-mile long South Carolina connected vehicle test bed, so this was our, the SETIT was the first tool we used to develop the plan for the project, the connected vehicle corridor that we implemented in Clemson. So this is a very convenient tool for connected autonomous vehicle research or deployment. So as I mentioned, that this SETIT ArcIT website will give you a good guidance on what standards exist for different applications. So in terms of messages, in terms of communication protocols, so which will be very useful for an ITS engineer. So now also you can find out easily what standards exist currently in terms of connected and automated vehicle safety, and different organizations, the standard body organizations are developing these standards. Some are already available. So here are some examples. So ISO 26262, road vehicles functional safety. So it deals with the safety design of automated driving. So it includes very rigorous requirements for automotive electronic systems. So it is safe when it is operational. Now the next standard ISO PAS 21448. So it is related to safety of intended functions. So this ISO 21448 was developed to augment the previous standard. So it includes the safety related to advanced driver assistance systems. So the ISO 21448 addresses specifically the advanced driver information system that are needed for validation and verification. So safety, and the third item, the ISO SAE, Society of Automotive Engineers 21434. So this is related to cybersecurity. As you all can appreciate, safety and security are interrelated. If security is compromised in connected and automated vehicles, then safety will be compromised as well. So it is very important when we are working on safety, we look at the cybersecurity aspect of connected and automated vehicles. As you can imagine, although connectivity is providing a lot of more functions to an autonomous vehicle, but it is also opening up a lot of attack surfaces, right? So now the outside entities can enter your vehicle system and corrupt your in-vehicle devices, in-vehicle sensors, in-vehicle network. So once we are making our autonomous vehicles connected, so our attack surfaces are increasing. So we have to look at cybersecurity as an integral part of safety. If cybersecurity is compromised, safety will be compromised. So we have to be very cognizant about this aspect. So now we'll talk about safety through different components of connected automated vehicles. First, we'll look at safety through connectivity or communications. So as we know that connectivity can be through vehicle to vehicle, vehicle to infrastructure, vehicle to VRU, or vehicle to vulnerable road users. And also we'll talk about how safety can be enhanced in addition to connectivity through the automation. that is why we are doing automation, right? So we are developing this automated car so we can take out the human error out of the system, but we'll see how safety will be enhanced by different levels of automation. So safety through vehicle-to-vehicle connectivity. So as you can see, I'll show it through a test we did in Clemson. And also you can find the detail of the test in the paper. I highlighted the reference citation on the bottom. So it has the detailed results of this test. So as you can see, the vehicle 1. So that is the red vehicle. It is showing the vehicle number 1, and then we have another vehicle number 2. Now in this case, the communication is enabled by dedicated short-range communication or DSRC, because for safety application, we need a communication medium that supports very low delay. So it should be 1 to 2 milliseconds, but at most it can be 200 milliseconds. So it has to be 200 milliseconds or less in order for the system to work. So for safety application, we were aiming to go below 200 milliseconds. So now you can see with the test. So the first, suddenly, for example, there was an object on the road and the first vehicle stopped. So if the first vehicle stops, then there'll be automatically a warning message to the second vehicle that collision ahead. Okay, so and then the second vehicle will have enough time to stop if we are using DSRC. So we tested whether the communication and the data warning generation, because the vehicle stops and there is an in-vehicle application running in the vehicle that is generating a stop vehicle ahead or collision ahead, and that is broadcasted. So the vehicle doesn't just target, okay, there is a vehicle behind it, so I need to send a message. It is always broadcasted. When the vehicle stopped suddenly, it will broadcast that collision ahead. So that is the standard, the 10 times per second, based on the SAE standard that we follow for safety. It will broadcast this information 10 times per second. So when a vehicle is within that communication range, which you can see with this circle, you can circle, that is the communication range of DSRC. So any vehicle of the first vehicle, the vehicle number 1, any vehicle coming close within that communication range and the vehicle stop, it will get a warning message. As you can see on the table, that the distance between, based on the different vehicle speed, so for the vehicle number 2 or the second vehicle, so the distance from vehicle 1 when the first safety warning message packet is received by the second vehicle, so that is the distance 272 feet, in the test run 336 feet, 308 feet. So we had enough distance. If you look at the third column, we only require 38 feet, but we have enough distance to stop. But for safety distance, 38 feet. When we were with 50 miles per hour, the vehicle speed, the second vehicle speed, you still see that our maximum distance was 355 feet, but our stopping distance was 240 feet. So we can, the second vehicle can safely stop. Let's look at another vantage point. So you see that, so the circle again on the left is the DSRC communication range, where the information is broadcasted. So it broadcasts the basic safety messages, the vehicle position, location, and so on. And also the warning as well, that collision ahead or suddenly a queue ahead, all this information will be generated 10 times per second. So on the right side, the graph, the upper right-hand corner graph, you see that this different speed, we have the message delivery time from vehicle 1 to vehicle 2. So from vehicle 1 to vehicle 2, what time it took. So we can see that it is like probably 90 milliseconds. and the maximum was like 130 milliseconds at different speed. But you see that for safety applications such as collision warning, we need 200 milliseconds. So we are doing much better than what is required for safety application. So now we were in the first, we were using CVT for the safety application, DSRC. But when we were using LT to send the message to vehicle 3, because vehicle 2, the vehicle 3 is outside this circle. Vehicle 3 is approaching the circle, but you see the it is kind of a light green. You can see on the legend, car 3 was using LT. So we need to do a couple of things. So we have to run multiple applications at the same time. When the first vehicle, remember the previous slide, stopped, it is sending a basic safety message to vehicle number 2 that is approaching, because now you need to give them a warning. But there is a vehicle that might be 1 mile away outside the DSRC range or 3 miles away, but you may need to give them a warning about an accident. So it could be a Q warning that, okay, there was an accident. Now the vehicle number 3 and beyond, you need to reroute or take alternate route. But you need to give a warning, but you cannot use DSRC at that time. So you can use LT because LT has a much larger range. So we are using LT. So you see that we were running, we are multitasking in terms of the message delivery. So we were running collision avoidance to vehicle within that DSRC range, and we were sending other information, for example, which is not safety critical, which doesn't have to be within 200 milliseconds. We were sending to vehicles outside the range. And you can enable that by running heterogeneous wireless networking. We'll talk about this a bit later. So for running multiple applications, you need heterogeneous wireless networking. So in the vehicle, so it will know that, okay, my safety message will go through DSRC, but non-critical safety message will go through LT or other communication mediums that doesn't give a very low delay to enable safety application. So the graph below, you'll see that the third vehicle, which is this light green, vehicle 3 LT, as you can see. So you can see, so the vehicle 3 is receiving warning like queue ahead. For example, there's a queue warning that there's a vehicle stops, a queue warning. So we're sending through LT. And in terms of the message delivery time, you'll see that it is much above 200 millisecond. So it is not, then we cannot use LT for safety, but we can use LT for non-safety critical application. So that's what we are showing here. But we were running multiple applications at the same time at a vehicle level. So now I'll talk some application on vehicle to infrastructure connectivity, V2I. So we did this application for intersection safety. So it is also known as stop sign gap assist application. If you look at the ARC IT I mentioned earlier, so it is intersection safety application, specifically stop sign gap assist. So we have a major road and we have a minor road. So the major road does not, a vehicle on the major road will not stop, but the minor road has a stop sign, so it has to stop, and when it says that there is enough gap, it will pass. But sometimes it happened to me too. I was on the minor road at an intersection in Ohio, but the side distance was not good. So I started, after stopping, crossing the intersection, and then I was hit by a vehicle on the major road. Probably it was speeding. So because of the side distance, I could not observe the vehicle on the major road. What happens if you have a roadside device, so that is transmitting a gap? So assuming that all are here are connected vehicles, so the connected vehicles on the major road will transmit data to the roadside device, and the roadside device will determine when there is an gap enough for the minor road vehicle to cross. And when it sees that there is enough gap, then it will inform the minor road vehicle to cross. So we saw a significant increase in safety by having this application running at an unsignalized intersection. And on the red, you see that the communication range of the roadside device. So here we were running DSRC. So that is the communication range. So any vehicle, connected vehicles within that, the red circle will get a warning or will be able to provide data. Warning for minor road vehicles, and will be able to provide data to major road vehicle. So now, also another application, vehicle to vulnerable road user connectivity. So in this application, you see that we were generating personal safety message. So according to the SAE standard, so SAE standard J2735, it is the standard for basic safety message. So for each vehicle, connected vehicle will generate certain data 10 times per second, vehicle location, position, acceleration, deceleration, speed. So those data will be broadcasted when they're according to this standard. And you can enable this standard, communicate via DSRC, you can do it via 5G or any other technology that you want to apply for your particular application. So now the personal safety message, which applies to pedestrian, they are a vulnerable road user. They follow the SAE standard J2945, which is actually based on the standard basic safety message standard J2735. So you see that what messages are generated or should be generated if you're following the SAE J2945, personal safety user type, timestamp, longitude, latitude, so the location, heading, speed, elevation of the pedestrian, where the pedestrian is, and the speed of the walking speed of the pedestrian. So so there are some certain messages that must be generated if you are following the J2945 SAE standard. Now, so you can use a device. So there are some commercial devices available, but that require a pedestrian to carry a device, and it will generate this information, speed, lat, long, and so on. But we expect that not all the time pedestrian will carry this device. It's like it's a box like you have for the connected vehicle device. So it is a device the pedestrian needs to carry. But we thought that it is not probably happen. It will not happen all the time. So what we did, we used a very inexpensive camera. So we deployed on our test bed. So, and it looked at the entire pedestrian, entire intersection. And so this low-cost video will send data to a roadside device, and it will analyze the video, this $50 camera data, and it will generate same type of messages that are required by SAE for pedestrian safety message or personal safety message rather. So we use this video and we generated an algorithm that by looking at the video, it will generate exactly the same messages that are required by the SAE. So we did that. We implemented at an intersection in Clemson, at an intersection in Clemson, and I'll show you. And this is an example where we are using this vehicle to pedestrian communication, vehicle to vehicle communication, and roadside to vehicle communication. So this is an example also of edge computing. So you can see that first, let's start with connected vehicle. Each connected vehicle at the intersection is sending data to my roadside infrastructure or roadside edge. So this is we have this infrastructure in the 3-mile stretch of the road at different intersection. So you have a DSRC device. So it can be a 5G device as well. So so 5G or DSRC device, and on the another box is showing a computing device. So we have to run some application. So we needed a computer. So we used TX2, a computer device for computing the application, running the application. And then we have these low-cost cameras, right? So this camera at the intersection, which continuously sending video data to my roadside infrastructure. So it has a radio to broadcast message and a computer to run the application. So my algorithm. So my PSM or pedestrian safety message generation algorithm is running in the data processing unit. So this is the NVIDIA TX2 device. So now, so once the video is sending data, so you see the video camera data via, here we were using wired communication. So we are using fiber optic communication, it is sending data here, but we can also do wireless communication as well. So we ran with both. Now, once the computing device generates a warning, so based on the data from the video camera and the data from the connected vehicle, so it generates a prediction that based on where the connected vehicle is now, where the pedestrians are now, what is the chance in the next timestamp there will be a risk of collision between the pedestrian and the connected vehicle. So now once we generate that, okay, there is a high probability that there will be an accident, then we warn the vehicles approaching the intersection, be careful, there is a pedestrian on your path, there is a high probability of accident. So you can give a warning to the connected vehicle. And also if a pedestrian is running our application on their cell phone, you can also give them a warning that just take precaution, a vehicle is approaching, there is a likelihood that you will be in an accident path with that vehicle. So this is the general framework of our edge computing. So, so the camera is sending data to the roadside infrastructure running the application and identifying, predicting the risk of collision. And then using the radio, 5G or DSRC, it is warning the pedestrians and the vehicles to be careful. So now, when we were running wireless communication, so the video, as you may recall from the previous diagram, the video is sending the video feed to the roadside edge. So what happens that if you're constantly sending video, that means that a lot of bandwidth requirement. So what we did, we developed another algorithm here. So we don't have to send the best quality video. So we looked at compressing the video with dynamic compression, lossy compression. So you see on the right, it is see there's video is running or not here now. So this is a real intersection at Clemson. So so for the first, the right hand, upper right hand, you see the without compression. But to save the bandwidth, we compress the video and we developed an algorithm based on the external condition in terms of light or weather conditions. So we compress the video so that we compress the video feed, but still we get a very reliable result. So we did that and we found that what is the optimal compression level based on the external condition. So, and we found that our pedestrian alert system works with very accurate result with compression as well, with this dynamic lossy compression. So it could have application in other areas too, whether you're using video for safety. So you can use the compression algorithms to make it work. So for our application, you see compare the pictures with the pedestrian so pedestrian location A. So the and A, B, C. So A is the pedestrian vehicle collision location. So this is what we will predict based on where the pedestrian is at this time, time t, and where the vehicle is at time t. We are predicting what will happen at time t+1, and we are continuously predicting the collision chances. So initially, the pedestrian started walking at the intersection, and the location B is when the vehicle, the connected vehicle, starts getting warning that you could be in a collision path with the pedestrian. And C is once you receive the warning, you'll stop at the intersection. So in our case, we did numerous field testing in several days in several lighting conditions. So you'll see that once the connected vehicle got warning, it stopped at location C, and the pedestrian location was A when the vehicle stopped. So there was no collision. So it ran very well. It was able to generate the safety warning. It was able to compress the video. And in all the cases, we saw the vehicle was able to stop. So they had enough time to decelerate and stop when they got the warning. So now what about latency, which is very important. We have to be on the very low latency. In the previous, I said 200 milliseconds for pedestrian, because we need to also run applications. So the alert, so our maximum allowable latency was 100 milliseconds. This is what we put our threshold as. So computational latency means that running the application, so getting the video feed and developing the alert that, okay, there is a high chance that there will be a collision between the pedestrian and the vehicle. So our minimum was 54 milliseconds to run the application in a TX2, NVIDIA TX2 device. And communication latency, once you generate the alert, how long it took for the roadside edge to send a warning to connected vehicle or connected pedestrian. So it was about 2 milliseconds. And maximum was 64 milliseconds for running the application in NVIDIA TX2, and communication was 17. So, and if you add 54 plus 2, so 56, which is below 100, and so for the maximum latency 2, so it is below 100 milliseconds. And the average we found was 56 milliseconds to for computation, 4 to communication. So on the lower hand graph, you see that the figure that the frequency. So the x-axis range of end-to-end latency. So that is the range 56 to 58 milliseconds, 58 to 61, and so on. And the number at the top of the graph is representing the frequency. So what we saw between 56 to 58 milliseconds, we had 10 observations. Between 58 to 61, we had 61 observations. Between 61 to 64, 80 observations. So above 80, we only had 1 observation. So we did repeated tests many times. So we had 1 observation that was above 80 milliseconds. So yeah, but it was still below 100 milliseconds for that case as well. So now we'll talk about the safety through different levels of automation. So this is the most recent automation level. As several of you may know, the Society of Automotive Engineers, they have different levels of automation from 0 to 5. And the arrow is representing as you're the downward, as we are going from 0 to higher number, we have a higher level of automation. So level 0, safety features are limited to providing warnings and momentary assistance. And examples of safety application for level 0, you can have automatic emergency braking, blind spot warning, lane departure. So as we are going from 0 to higher level, our safety is increasing. Our safety features are increasing, and we have a higher number of safety applications, or more detailed safety applications. So our autonomous vehicles are getting safer as we are going to a higher level of automation. For example, the level 4 automation, as you can see, the vehicle can drive itself under limited conditions and will not operate unless all required conditions are met. So, and then there are some safety associated with traffic jam assistant. And so you can have local driverless taxi, and pedal steering wheel may or may not be installed. So you may still need a steering wheel and brake devices to press the brake device at the driver level. So it is automation at some situations. But level 5, it's fully automated vehicle. So you virtually may not need any steering wheel or brake for the driver to engage brakes or use the steering wheel. So when we go to level 5, as we are taking out all the decision making out from the driver, so we expect it to be safer than the lower levels of automation. So that's where we are heading, and the motivation is, as always, safety, to have a higher level of automation. So yeah, so the safety features and example applications are listed here for different levels of automation. So now it's all good. So we know that connectivity helps with safety, automation helps with safety, but there's some solutions to connectivity and automation. So we also need to address them as we are working on safety uh, through connected and automated vehicles. We also need to look at what are the challenges. So we need to consider them simultaneously so we can have a comprehensive level of safety in our future transportation system. So some challenges to connectivity. As I mentioned earlier, security could be a major function of safety and vice versa. If your system is not secure, it will not be safe. So we have to be cognizant about security. Now, one thing we have to be worry about is security violation or security attack or cyber attack through connectivity. As you have learned in the recent days, that cyber attack is a major issue. So, your vehicles will be computers, right? A connected automated vehicle will be a computer on wheels. So it will have the same vulnerabilities, could be sometimes even more, because you have more attack surfaces with this connectivity with different entities. So now I see a major threat when your transportation cyber physical systems are connected with other cyber physical systems. So as you see that I have an example that the building cyber physical systems and electricity grid cyber physical systems. So when we say cyber physical systems in an area, for example, cyber physical system for transportation, so the communication is vertical. So there are 3 layers in cyber physical systems: sensor and actuator. So it's sensing, it is functioning, it is providing the sensing function, and you have a communication function, and then you have a computer control layer. So you have a sensor layer, you have a communication layer, and the compute layer. So vertically within a CPS, they are communicating vertically. But so there is a safety security risk when they're communicating vertically. But even the danger could be significant when they're communicating horizontally. So, so what is the difference between IoT, Internet of Things, and cyber physical systems? So in cyber physical systems, your communication is vertical between sensing and your compute through any communication medium. But in IoT, different cyber physical systems are communicating horizontally. So when there is a horizontal communication, it is Internet of Things. And when it's vertical, it is cyber physical systems. So when we see a horizontal communication between different cyber physical systems in a smart city, we can expect much more cybersecurity risk. So we have to be very cognizant and involved in research and development, how to protect the Internet of Things in a smart city. So protect the cyber physical systems of transportation, as well as the Internet of Things that are connecting between different cyber physical systems in a city. So we are looking at how the threat can propagate. If one cyber physical system is attacked, it might be propagated with other cyber physical systems. And if we cannot protect our cyber physical systems or Internet of Things, all the communities or the end users, as I listed below, will be impacted. So our city population, rural community, everyone will be impacted in our society. So now this is a very recent news. So I mentioned all the good things that the connectivity can provide in terms of collision avoidance, in terms of increasing safety. So we had seen a lot of work in connectivity, vehicle to vehicle or vehicle to infrastructure, especially for safety through DSRC. But on November 18, 2020, So DSRC, the rule changed, right? So under the new rules, DSRC is to be phased out over the 12 months after after this report, and then is expected to be sometime in in 2021 that will have this DSRC being phased out. So the spectrum that was dedicated to transportation will no longer be dedicated to transportation. So it is given to so there is a portion that will be provided for the unlicensed band, and another portion will be open to transportation and other applications. But so what we do now with DSRC being phased out, it will be replaced by C vehicle to everything communication, or cellular vehicle to everything communication. So now there is a concern that once the DSRC is no longer dedicated to transportation safety, what happens? So the solutions could be in cellular V2X and heterogeneous wireless networking. So as I mentioned, so you need to, the vehicles or roadside device need to know what communication medium to use at for what applications. This is one example of heterogeneous wireless networking. As you can see, when there is a major crash, there is a fire, there was a major accident happened. So the vehicle received a warning that there's a major crash. The first vehicle, the first dark blue vehicle. So what it's doing, it is using C, you can see the legend on the bottom, C, cellular vehicle to everything direct communication, and cellular V2X network communication. So the difference is C V2X, or vehicle to everything communication, direct communication, doesn't go through any cellular tower or any base station. It directly communicates with the vehicles close to it. So you see that the communication is going on the dark yellow through C V2X direct communication. It is not going through any cell tower. But now for a safety warning, collision warning, you have to run it through C V2X direct communication. But the item that can absorb higher delay, that can allow higher delay, like Q warning, you can then send it through a cell tower. So it is, you can use the V2X cellular communication. So network communication, you can use 5G communication. So it can go through a cell tower, and then, but it will be, there'll be time added, right? Because it's not a direct communication. So you can run multiple applications if the vehicle, all the vehicles are running heterogeneous wireless communication. So it knows for safety, I have to use C V2X direct communication. For non-safety application, I have to use maybe LT base station or 5G base station. So, and again, like for vehicle to vehicle direct, so for safety, you use that. But for just for information sharing, which is not safety critical, use C V2X network communication. So now this will be a now major part of our safety of connected autonomous vehicle. So we have two modes, direct communication and network communication mode. DSRC, the difference between DSRC and cellular V2X, DSRC uses a wireless standard called WAVE, while CV2X uses three GPP standards such as LTE, 4G, or 5G, like cellular phones. So for direct communication, like DSRC, it runs on 5.9 gigahertz spectrum. And so it has a very low delay associated with it. Either you're communicating with the traffic light using direct communication, or with other vehicles or any other roadside device, you'll use 5.9 gigahertz. So the delay is very low. So you can, it will meet the safety requirements if you are using direct communication mode. The delay will be similar to what we have seen in DSRC. It can vary from 1 millisecond to 2 milliseconds to 50, 60 milliseconds. So the delay will be similar. But when you are going towards the network communication mode, so either you have 5G or LTE. So the vehicle is first sending to 5G cell station or LTE tower. And through that, it is going to its intended recipient. Either it's a traffic signal or it's another vehicle far away. So you can see that it has to go through a network. So that's why the delay is higher. So now 5G will be a major part of connected automated vehicle safety, and it provides a lot of opportunities for applications in transportation system for its safety and also mobility. So there are three types of 5G spectrum. We can divide into three categories. Low frequency cells, which is less than 1 gigahertz. As you can see, the purple color, you can see that it has a higher range. So the lower your frequency, you'll have a higher range. But so, sorry. And the high frequency cells, so 1.1 to 6 gigahertz. As you can notice here, so the 5.9 gigahertz is here, right? So if you want to run C-V2S direct communication, then it will be in the high frequency spectrum. It has to run specifically at 5.9 gigahertz. So it has a higher frequency. So you can send more data with a high frequency. And the millimeter wave, you can also apply for transportation, but the range will be lower. So, and we can see that what are the applications of higher frequency can cover like a stadium with a high frequency millimeter wave. So a lot of data transmission. For vehicle communication, so you can, so if you want to use the safety application, so you have to use the high frequency because it's a follow 5.9 gigahertz. And for low frequency, you can cover a city with a low frequency with a couple of towers, cell stations. So for safety application, 5G provides a great opportunity. It offers a unified network architecture design, which uses a wide range of frequency bands for different applications by sharing physical network infrastructure through network slicing. What it means that you can use the one cell tower to run different frequency of applications. So you can run a safety application, you can run a mobility application, and so you can run different types of application with one cell station through network slicing. Now, some challenges to automation. So human-machine interface. So how human will interact with connected and automated vehicles, especially from level 1 to 4, there's some human involvement. So how they will interact with those different levels of automation, that needs to be studied. It has been, there are some studies going on by different auto manufacturers at some research institutions, but it needs to be looked at more carefully. At level 5, when you're fully automated service, so how the occupants will need to behave. For example, to initiate the autonomous vehicle, do they need to do something like password or something? So if that happens, how different types of users can interact with the fully automated vehicle, whether it will open up some cybersecurity risk. We know sometimes there are a lot of problems with password protection and software updates. So we need to consider different types of users in the society and how they will interact with the different levels of automation. Now, we have done some research on technology failure for autonomous vehicles. So the sensors that we have on autonomous vehicle can fail. There is a likelihood that any of the sensors that help us to run the autonomous vehicle safety can fail, and the probability is not very low. So how we make sure that this doesn't happen, especially when the autonomous vehicle is running in mixed traffic. Now the third item, critical locations. So if you think autonomous vehicle, so for a straight freeway section, say in level 4 automation, that can work pretty well. But at critical location, for example, especially when autonomous vehicle is changing lanes or trying to merge on the freeway. So there are a lot of locations on the highway that autonomous vehicle operations or safety could be challenged. So we need to look at those critical locations where the operation of the autonomous vehicles will be challenging, which will compromise safety. The next item, situational awareness. So this is also very important. Now, when we have a robot driving the car, so we need, it's not looking at the world like human drivers will see the world. So we need to give it some awareness of what's going on. So for example, when there are a lot of vehicles around an autonomous vehicle, non-autonomous vehicle. So for example, aggressive drivers and different types of situation that is occurring around it. So if it just goes based on the data from the sensors, then it might miss out some information for it to drive safely. So it needs to have some understanding of the situation beyond the sensor. So we need to have some intelligence in it to understand how the environment is working around it, so it can make more human-like decision. So under non-normal situation. So as I mentioned earlier, so security is related to safety. So one thing that autonomous vehicle will use is artificial intelligence or AI. So yeah, it's good that we are using AI to do great things, but how you protect the AI? So if someone is attacking your artificial intelligence system in an autonomous vehicle, that could create a huge problem, as you will see shortly. So this is one major area that we are working on, which is adversarial attack. So you can see that an attacker can go into the autonomous vehicle. Okay, the autonomous vehicle, the neural networks, so it can embed some noise in it. And so if you have a stop sign, it will recognize it as a 45 miles per speed sign. Or if you have a 25 miles per hour speed limit sign, you can have a targeted attack. So there could be two types of attack. Targeted, so you want to change the speed sign from 25 in the perception module of autonomous vehicle to 45 miles per hour. So, and then if that autonomous vehicle drive at that speed, that could be a risky situation in that speed zone. So adversarial attack, this is called adversarial attack. It can compromise the artificial intelligence of autonomous vehicle and cause severe safety consequences such as crashes. With cyber attack that we are seeing today, so it might be more important to protect the autonomous vehicle. And so targeted attacks, you can change the perception module to anything you want, a stop sign to 55 miles per speed sign, or anything, or a 25 to 75 miles per hour. And there's an untargeted attack. So just the attacker just targets the autonomous vehicle system, and they don't have any target that they want to system to perceive at certain the recognition module to certain things. So for this example, the autonomous vehicle video camera, which sees the traffic signs, so it is seeing the video is seeing a stop sign, but the perception module in the vehicle is attacked. The AI inside the vehicle is attacked, and it is recognizing at 45 miles per hour speed limit. So it's a misclassified traffic sign. So we did a research with the LISA traffic sign database. It is a set of videos and annotated frames containing US traffic signs from different cameras. So it has 47 different US sign types, 7,855 annotation, and it has different types of data, as you can see here, the metadata. So what happens when we attack the 35 miles per hour speed sign? We did field experiments, and we were able to change it to do not enter, 45 to stop, and the pedestrian walking to a different sign. So you can see, and we were able to do that extremely easily in the field. So when we ran different autonomous vehicle attack model, so our cyber attack model, we use this popular three types of attack, CNW, FGSM, and BIM. And you can see that that once we attack the average success rate, so for the carbless left sign, we were 100% successful in changing the sign to something else, right? So we can say we can say speed limit sign or a different sign. So, and for the carb right, we were very successful. So based on our field experiments, this is what we found, that how many times we were able to fool the autonomous vehicle perception module. So when the sign was carved left, it was seen as something else by the autonomous vehicle. So we can see that how easy it is to do the attack on the AI of an autonomous vehicle. So, and then when, as I said, that it is based on our field experiments. And so you see that we were showing to the audience, like, all the tests that, okay, we have a video showing stop sign in front of us, but it is showing as a 45 in the autonomous vehicle recognition module. So if it is stop sign, the autonomous vehicle will think it's a 45 miles per hour speed limit sign. So we ran the application, the autonomous vehicle application, in our NVIDIA TX2 device, as it says here. So we are working on protecting the AI for autonomous and connected vehicles. So what we are doing, so here we have the input image from the video camera in the autonomous vehicle, and we are creating a grid of the traffic sign and divide the image into a certain number of blocks. And then we are doing a random patching of several blocks from the image grid. And then we are, so once we are doing this patching, so we are taking like several segments in the vehicle, and we are training our neural network, not for just the stop sign, but the segments. So we are training to recognize the stop sign by recognizing the different segments of the autonomous vehicle. So we are doing random patching in this case. So we are training our CNN with the different segments of the image. And then when we are, our camera is recognizing the image, it is not looking at just the stop sign as a whole. It is detecting different segments of the stop sign and recognizing it by the different segments of the stop sign. So we have seen, initial result that is a lower chance of getting compromised through adversarial attack. So one thing that we are doing now at C2M2 is the digital infrastructure for connected autonomous vehicle safety. So you have to include the societal system in it. So we all are familiar with the transportation cyber physical systems, but we need to include, especially for safety and security, the society into the equation. So when we are running any connected and autonomous vehicle applications and running in a connected corridor in a smart city, we have to have a constant feedback, as you see on the left side of the figure, from the users. So what the part of the society, actually, different types of users, different age groups, with different needs. So they will provide feedback to our cyber physical systems. So this is our backend infrastructure, as you have seen the IoT diagram. So so this is our compute device, the backend infrastructure, backend computer, and then we have the sensing devices, this multimodal transportation system and different sensors. But now we are adding society as a data source. So they are providing continuous feedback to our cyber physical systems. So now when we were doing this testing, so we are involving the entire community around our test bed. So so for collision warning, we are using C-V2X direct communication, and then we are using for Q warning, we are using LT tower, network communication, and then also we are continuously receiving input from the users, so whether what they find useful, what they find not useful, and so we can continuously modify our system. So our goal now is to develop a transportation cyber physical social system, so that we have input not only from our transportation system, but as well from all users in real time or in near real time. So now those of you who are very interested in working in a transportation cyber physical social systems, so you need to understand the cyber system, so understand the computing aspects of it, and then the physical system. So as a transportation engineer, so most of us are well versed in it. And also we need to get well versed in the social system. So how these three components work together to make our transportation system safe and secure. So if you want to run this type of application or develop a system like that, or want to work in this area, you need to know some programming skills, MATLAB, Python, or C++. So if you say, okay, I want to know exactly just to say one tool I need to learn to work in this area very well, so I'll say Python. So you'll see that there are several online training courses available in Python. So that will be very useful. Also, our center offers Python course for free. So and also we show how you can apply Python for connected and autonomous vehicle applications. You can let us know. So we offer from time to time free course on Python for connected and autonomous vehicles. So we can give you information when to attend or how to attend our courses. So there are some courses that I encourage my students, my mentees to take advantage of. These courses are free most of the time, with some type of like a free request for funding. So Udacity, Coursera, EDX, IBM Research, they offer free courses. So another skill you need to know, the edge computing and cloud computing. So those will also come handy, especially if you know how to use Amazon Cloud, Google Cloud, or IBM Cloud, or any of the cloud services. That will be very good for transportation, cyber physical, social systems. My last point, the real world experience. So get involved, like when we have our test bed, in addition to a corridor, you have several other test corridors that we are involved in, and we involved this upstate Greenville Pickens area testbed cluster. It's a community of 1 million people. So this forms our IoT testbeds. So if you have a chance to work in the real world, so you get a lot of experience through that. So that was my experience with my students. They learned a lot by working on these cluster testbeds. So now I believe that now we are advancing a lot on the vehicle side, connected and automated vehicle operations. But at the same time, the public agencies need to build the digital infrastructure. It could be in cooperation with the private enterprises, but they need to develop the digital infrastructure to support the CAV operations that will enhance our safety, transportation safety and mobility. So this is the end of my presentation, and I'll be very happy to entertain any question you have. Charlotte, you will you let me know if there's any question, please.
Yes, it doesn't look like we have any questions in the chat currently. If you have a question, feel free to ask it, or you can unmute yourself and just ask it directly. While we give people a minute, as with all of our distinguished speaker chats, we will have a recording of this available on our YouTube channel and our website, and those will go up a little bit later this week.
Any question from the audience?
Hi, Dr. Chowdhury. Thank you very much for the presentation.
Yes, thank you.
I would like to ask when this communication, when it's not dedicated anymore,
right?
Or did I understand that correctly? Or if it's not dedicated anymore, would there be some issues, in terms of authentication, and it's almost like any interruption and those kind of stuff?
No. So yes. No.
Yes.
Sorry, do you have any other additional? So I can answer what you said.
No, that's basically my question. I kind of wanted to ask you. Yeah.
No, so it will be kind of dedicated. So what it is going on, that if you have this C-V2X direct communication in your vehicle, it will act like your DSRC. So if you have another vehicle with this technology, it will they will be reliably communicate. So the standards are not going away. This the information, how the information will be broadcasted, and so it will not be. It will be there. The standards will be there, and it will run in the same communication spectrum. But the only difference is the protocol. it's just changing at the protocol level. So so the DSRC was running on wave protocol, but it is running on a different protocol. So 3GPP. So only the protocol is changing, but the reliability will not change.
Okay. Thank you.
Yes. Thank you. Any other questions?
I don't see any other questions. I have put a link to our website in the chat box.
Okay. All right, then thank you all. Thank you for listening to me. Charlotte, thank you. Charlotte, Saqib, thank you.
Thank you, Dr. Saqib, for your awesome presentation. Very informative.
I'd like to thank Dr. Saqib Khan, who actually was a part of all the research I'm discussing. He is a part of this research that I'm presenting today. Thank you.
Thank you. Thank you.